Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is, till now we understand what are the various practical issues what we understand in our as per the hydraulic modification techniques. See, in this different techniques we will see in our previous lectures. In this, what we understand, we are understanding the problem statement. So it may give what type of the soil or what kind of situations we are there for getting the technique. We are using that particular technique. So what is the expected outcome we are getting for the technique. So those kind of problem statements we will understand, and according to the what are the steps involved according to the problem statement involved as per the modification technique. So in this, the problem statement, the one is design a pre-loading and vertical drain system to consolidate. So here we required the consolidation, and also the pre-loading and vertical drain is the techniques. The two for type of the soil already mentioned here, that is clay soil. It depends upon the type of the soil, and also we choose the technique. So here we are going to understand the design a preloading and vertical drain system to consolidate a 100 to 100 area of the soft clay soil. So to a depth of 100 meter to 100 meter area. So the area they mentioned about this clayey soil, soft clay soil to depth of 10 meters. So to up to in this surface, this area 100 meters to 100 meters. So the soft clay to depth of up to 10 meters. So the initial void ratio is 1.5 meters and desired final void ratio is 1. So here the initial void ratio is 1.5. So before construction work the void ratio is 1.5 and we required the final void ratio is 1.0. So assume the coefficient of consolidation. So we have to know some of the parameters that we assume. In practical we may understand and we do some laboratory test for getting the required property of the particular soil. So here what we understand, that is we are going to do this consolidation for this particular technique using the technique. So here the average permeability is also we are going to understand. So these things we are going to get according to the soil property. So here what we assume, it depends upon the soil property. So according to that we are going to understand this average permeability. So here what are the steps involved for getting the required or desired void ratio, that is 1.0. For this the technique which we choose is the preloading and vertical drains to consolidation. So then only we will get the void ratio. Here to determine the final and initial volumes of the void. So here initial volume of the void is 1.5. What are the desired is equal to 1.0. And here the first thing we have to understand the volume of the soil. So it depends upon the area multiplied by depth. Area multiplied by depth. So here volume is equal to, we'll find out. Now initial volume voids. So here initial volume voids is equal to, so volume of voids, that is equal to total volume for this initial volume of voids, total volume multiplied by how much the volume it is there, and also addition of the required and also the initial void ratio, that gives the volume of initial voids. Now and also find out the volume of voids final. So here we are going to understand the required volume of voids divided by the total. So by the initial voids and also the final voids. So here now how much volume of volutes is going to reduct, that is equal to 10,000 meter cube. So here initial volume of voids, final volume of voids. So how much we are going to require to get the volume reduction, that is equal to, so we are going to subtract from one each other. Now the next step we are going to understand, here we are using vertical drains. So here determine the time for consolidation using these vertical drains. So coefficient of consolidation, drain spacing is the important patterns. So here we choose the square pattern for doing this process. And this coefficient of consolidation is 2 into 10 to the power of 7 meter square per second. So using Baron's equation for radial drainage, so that is equal to that formula we use. So 4 into time by 8 square. So it's time to achieve 90% of consolidation. It depends upon the voids, how much we reach. It depends upon the percentage of consolidation. The time of consolidation finally we'll get, it requires 80 days for this volume. So for getting this like this, we are going to understand the, and it is whether it is suitable or not for the required project. It is depends upon the various parameters. Now here the problem statement, we are design preloading and vertical drain system to consolidate. Here these vertical drain systems, how much time it is required. So we are doing for this problem statement. And also move on to the another kind of problem statement, that is sand compaction piles for loose sand. So in this sand compaction pile system, to improve the bearing capacity of, here also they mention the area, that is equal to 50 meters into 50 meters. It's a square area of loose sand at a depth of 15 meters. So the initial relative density is 40% and the target relative density is 70%. Here what are the steps involved in this particular problem, that is determine the required increase initial strength, volume of the sand and design sand compaction piles. These are the step by step procedure which is involved. In each steps what we do the calculations, we will check in this problem statement, that is determine the required increase in density. So this initial density is 40%, the required density is 70%. The difference between the density is equal to 30%. So initially it is 40%, it is there. The final relative density is 70%. The difference between those two is 30%. Now volume of sand to be compacted. How much volume of sand to be compacted in this particular? So the first we have to find out the total volume, that is equal to area 50 into 50 and multiplied by the depth, that is equal to 15 meters. So finally this is the volume of the total sand. So in this we are going to compact. So this volume we are going to compact it. So in this, the design of sand compaction piles. So diameter of the pile we assume that is equal to 1 meter. Spacing of piles is assumed 3 meters in a square pattern. So now we are going to find out the number of piles per side. So here each side is equal to 50 meters and the spacing is equal to 3 meters, that is equal to 17. So total number of piles is 289. Now volume of each pile. So volume of each pile is equal to, so we already assume these things. So now, so this is the volume of each pile. So according to that we are finding the total volume of the piles. Like this we are going to understand this compaction piles per loose sand. So these are the in sand compaction. This particular problem statement, these are the steps involved, that is how much required of the property, whether it is may increase or decrease, whatever it may be. So the difference between the initial and required, initial state and final state, that is the important thing. So now, and also find the volume of the sand, total volume of the whatever the area, and we are going to find out. Now design a sand compaction piles. So according to that we are going to design how many number of piles are required for that particular project, and also the volume, total volume of those piles. These are the steps involved in this particular problem statement. Now move on to the another kind of, that is electro-osmosis for fine-grained soil. So here we understand, we choose the technique, that is, we choose technique is the electro-osmosis, and for the type of the soil is fine-grained soil. Calculate the how much time is required to dewater. So here 40 by 40 area to depth of 5 meters using electro-osmosis. The electro-osmotic permeability, that is equal to 5 into 10 to the power of minus 9 meters square per voltage per second, and applied voltage gradient is 2 voltage per meter square. So like this we are understand the what are the things involved in this particular problem statement. So we know which technique we are using, that is electro-osmosis, what kind of type of soil is involved, that is fine-grained soil, and also the depth, how much depth of the, and depth and area where we are using to get the dewater that particular area, and also along with the depth using this technique. So here they asked about the how much time is required. For the what are the required parameters, they already mentioned. If not mentioned also, we know the soil. So from in practical, what we'll do, we'll go those site and we'll collect the sample, collect the soil sample, and we'll do the what are the required parameters are there, and also the we collect the soil sample and we are going to do required tests for getting the desired properties of the soil. So here what we are going to understand, that is equal, here we are going to calculate the time, what is the required for the dewater of this particular area, and along with the depth using the particular technique, they mentioned about the technique, and also the parameters which are required for this, including of how much voltage gradient we are applying for that particular, for reaching the dewatering in that particular system. So here, without knowing of in few of the properties are also may miss in practical solution, practical problems when we are considered. So there we are going to collect the soil sample and we are going to done the required test for getting the desired properties to know about the soil condition. So these are the things we will do in our practical issues. Now here they asked regarding the time, how much time is required only. So now we are the first step what we do, that is equal to volume of water is to be removed. How much volume of water is to be removed. So here volume of water. So that area is equal to 40 meters into 40 meters and the depth is equal to 5 meters and the volume is equal to 40 into 40 into 5, that is equal to 8000 meter cube. That flow rate, that is equal to discharge. That flow rate is nothing but the discharge. So here we are, the next step for the first one we are going to find out the volume of water and the next one is equal to flow rate. For finding the flow rate in electro-osmosis using technology. So here first we know about the electro-osmotic permeability and applied voltage and cross-sectional area. These are the parameters first we understand for know about the electro-osmosis for fine-grained soil. Now this is the formula we choose, that is equal to QC. This is the permeability of the electro-osmosis, area and voltage gradient. We are going to apply this voltage gradient. So this is the formula. We are applying all the numerical values. Finally, we will get the discharge. Now after we know the volume and the discharge, how much time is required for this dewatering, that is equal to time T is equal to volume by the discharge. So that volume by discharge gives the number of days. How many number of days is required, for that we will know according to this. So like this we are going to understand the problem statement which is given. In this, and one more kind of problem that is equal to vacuum consolidation for silty clay. Here vacuum consolidation is the technique which we choose for getting the required properties of this type of soil, that is silty clay. Silty clay. So here the given, we are going to design a vacuum consolidation system. Here they are asking about we are going to design the vacuum consolidation system to improve this area of silty clay at up to the depth of 8 meters. The initial void ratio is 1.2 and the final void ratio is 0.9. So the coefficient of consolidation is also mentioned. If not mentioned, we are collecting the soil sample, we are doing the required laboratory test, or we are conducting on-site tests also, in situ test or laboratory test. Which one is suitable for the know about the property, to know property. So we are doing the process also. Here, as per the problem statement, we know the coefficient of consolidation, that is equal to 3 into 10 to the power of minus 6 meters per second. Here the step 1 is determine the initial and final volumes of the voids. So initial volume is 1.2, final volume is equal to 0.9. This is nothing but what we required for the before construction of the project. So for that particular soil, before how it is there, so we are going to prepare the final volume void ratio is equal to 0.9. Here volume of the soil, the first step we are find out the volume of the soil. According to that, we are finding the initial volume of the voids and final volume of the voids. The difference between those two gives the how much volume we are going to deduct for this using this vacuum consolidation. So using this system, we are going to deduct this much volume. So how much already it is in the state of 1.2 volume of void. Now we are reducing into the 0.9. So finally the volume of reduction is equal to the difference between the initial and the final requirement of the volume of void. So finally this is this much volume we are going to 519. After calculation we will get the 519 meter cube is the reduction volume which we required. So here determine the time for consolidation. So this coefficient of consolidation already mentioned in our problem, that is 3 into 10 to the power of minus 6 meters per second. Here we are using Trege's 1D consolidation theory. Using that we are finding for achieve 90% of consolidation, not for 100% consolidation. For reaching the 90% consolidation, we are using this formula. Finally, we will get how much time is required for getting the consolidation. So like this, we are understanding the problem statement. These are the things involved in this vacuum consolidation for silty clays. So here what we understand, what type of soil is there, which type of technique we are choosing, what type of soil is there is the important parameter. So like that we are going to design according to the statement. Now here the another kind of technique which we use, that is cement grouting for gravelly soil. So here the technique is, this is the technique which we choose for getting the desired properties of the type of the soil, that is equal to gravelly soil. So here design cement grouting systems to stabilize. Here what is the required thing is the stabilization. Previous what we done, that is the consolidation. Here it required stabilization to area of 20 meters to 20 meter area of gravelly soil at the depth of 6 meters. The grout injection rate is also mentioned, that is equal to 0.5 meters cube per minute per hole. And the spacing between the hole is 2 meters. Now the step-by-step procedure, volume of soil to be stabilized, that is equal to area is equal to 20 into 20 meters, depth is equal to 6 meters. So we are calculate according to the given data. So finally we will get the volume of the soil to be stabilized. So here number of grouts holes. So here we are going to consider 2 meters. The spacing between holes is 2 meters, that too square pattern. So number of holes per side, that is equal to 20 by 2, that is equal to 10, because that one side of the that square pattern is 20. And after that the grout volume. So we are going to injection the grout rate, that is equal to 0.05 meter cube per minute. So finally total injection time per the hole is equal to the 33 days. Using the calculations we will get this total injection time per hole, that is equal to 33 days. So like this we are going to understand the how much time is required for this cement grouting for gravelly soil as per the given data. So these are the various techniques which are involved in this hydraulic modification to get the desired property. So these are the various problems which we face and what are the various techniques involved for based on the type of the soil we are going to choose. These are the various things which we are involved in this hydraulic modification. In overall summary, what we do in this hydraulic modification, that is preloading and vertical drains of clayey soil. In this method, we are applying external load to accelerate the soil consolidation. These vertical drains enhance the process by providing pathways for water to escape. And the next one is sand compaction piles for loose sand. So here the sand compaction piles technique is used to improve the density and bearing capacity of the loose sandy soils by driving the sand into the ground. In electroosmosis for fine-grained soil, electroosmosis involves applying an electrical field to move water through fine-grained soils, aiding in dewatering and soil stabilization. In vacuum consolidation for silty clay, vacuum consolidation uses vacuum pressure to induce consolidation into silty clay soil, reducing void ratios and improving soil strength. In cement grouting for gravelly soils, cement grouting stabilizes the gravel soil by injecting grout into the ground, filling voids and binding particles together. So in each, what type of technique it is, what kind of property it is going to be modified, on which type of the soil. These are the major parameters which are going to involved in this modification techniques. So few are there. So these are the some of the techniques we will discuss in our previous lectures also. So like this we are understanding the what type of, according to the type of soil, what kind of improvement is required is given to the method of the technique. So these are the things which we are going to understand. Thank you. We will see in our next class.
Like, share and subscribe. Hit the bell icon for more updates.